If okay, now it started.
This is our presentation of our machine learning project on the auto-segmentation of knee cartilage from magnetic resonance imaging with Adam and Lincoln. So total knee replacements are an incredibly common medical procedure. There's about 9 million people currently in the United States who have received a total knee transplant, and about 10% of people in this country are projected to receive a knee replacement in at least one point during their lifetime. But we know that the structure of the knee joint really affects patient recovery, patient outcomes from surgery, and also the development of osteoarthritis after surgery. So it's a really important thing to study, and we're able to study joint structures using magnetic resonance imaging, also known as MRI. So the first step in analyzing MRI is a process known as segmentation. Segmentation is the identification of regions of interest from your image. There's an example of that in a lung CT scan shown on the right, where key parts of the lung anatomy have been identified. And we need to do something similar to our MRIs so that we can identify structures within our image. In this case, we want to identify the cartilage. Segmentation is typically done manually, but that's very slow and resource intensive because someone has to manually go through each slice of the MRI and segment out the desired structures. So ideally, we'd be able to do this automatically in a really efficient and accurate way, since segmentation is needed for studying all the outcomes we previously discussed, as well as planning surgeries, making diagnoses, and many other things.
Yeah, so as far as relevance goes, in terms of how important segmentation is, the segmenting of the cartilage can provide us with a good amount of insight towards the patient's recovery, especially like the prognosis, how their cartilage is healing, whether or not they are at risk for arthritis or even possibly even cancer. But the whole goal is obviously to do this as efficiently as possible with machine learning. But segmentation in general is a really big clinical marker for patient recovery after total knee replacement, which is the big important thing here. So for our data set, we can't really talk about it too much. We can only talk about details because we have to follow HIPAA. It's actual patient data from a lab here at UVM in the hospital, the MyOB lab, Musculoskeletal Imaging and Orthopedics Biomechanics Laboratory. But essentially, it's a 20 by 15 by 512 by 512 by 64 array. 20, the first index being subject's number, and then the next two obviously being the pixels, and then the last one being the slices of those pixels to eventually form the full 3D thing. And so our goal is that we would throw in these raw MRI data of someone's knee, and we would be able to get these right here, these cartilage masks. So another 3D model of that person's cartilage. And we can use it to calculate a lot of stuff like where force is being applied, what areas are wearing off more than others, because normally you'd come in and every few months and get an MRI. And yeah, so here's yeah.
We implemented a few different ways of doing this. The first one that we looked at is called UNet, and this architecture is one that's pretty commonly used for medical image analysis. So UNet kind of has three main components. The first is the contracting pathway, which downsamples your images through a series of convolutions and poolings. And then the next is an expansion system, which upsamples your image back to the original size using upconvolution. And then there's also a series of skip connections. These skip connections kind of connect the output of some of the contracting layers to the more expansive layers. And this allows later layers towards the end of the network to access information about those features from the very beginning of the network. And it makes it a pretty effective tool for image analysis. And for our network, we decided to kind of simplify things by taking our MRI, breaking apart the three-dimensional stack into two-dimensional slices, identifying the cartilage in each stack, and then recombining the images into 3D. So on the left here, you can see the plot of the loss over the training time. And we used here binary focal cross entropy loss because we wanted to put more focus on the true positives than the true negatives. And the reason that we did that is that in our kind of desired output, the samples are really skewed toward more voxels, which represent not cartilage than cartilage. And so we wanted to use the focal loss function instead. And then on the right, you can see the output from our UNet. So the first column shows the slices from the MRI. So that's actual MRI data. The middle one shows the expected mask, and that was given to us by people in the Myobe lab who actually went through and segmented all these MRIs manually. And the last column shows the predicted masks. And we can see that it matches pretty closely, but there are definitely some places where the model's still making mistakes, and this was about 98% accurate. One of the most difficult parts about the UNet architecture was choosing the threshold, which was our cutoff value for whether or not we decided that something was or was not cartilage. And at first, we just looked at the effect of the threshold on accuracy, but there wasn't a clear like best threshold to choose from that because it was basically either choosing between an accuracy of almost zero or almost one. But we were getting a lot of false negatives when we did that. So we switched instead to the precision recall curve, which is shown on the right here. And here we chose the threshold that gave us the highest product of precision and recall to get a trade-off of true positives and true negatives.
Okay, so now we used for our second algorithm, we use this really big open, what's it called? Open source medical imaging network, essentially called MONAI. And essentially it's this, they have this whole package and a bunch of different types of algorithms. They call them like swim unit R, which is a type of UNet. They have like um, SegResNet 2D, SegResNet 3D. They have a bunch of different algorithms, and what you do is they have this pipeline where just with a good amount of syntax, nothing crazy. It'll analyze the data for you. It essentially selects algorithms. Normally, it has four default ones, but for this one, we use DINTS and SegResNet because those are the ones that were mostly correlated to like knee imaging based on the papers we were reading. And essentially, once you pick the algorithms, it'll generate and train the algorithms on data and then it will either optionally you can like optimize the hyperparameters, but then after it trains the models, it's going to rank each algorithm based on its performance on the data, and then it's going to take the best algorithm's performance, and it's going to gonna use it on the unseen data. So that's like the general gist of what Mana is good at. It's pretty good at it. So results. So the first one on the left here is they're all with epoch, 6 epochs. But essentially what you do is in order to organize your data, we split it up. We split it up 20% testing and 80% training because we don't have a huge data set considering a lot of other MRI data sets have hundreds and thousands of different images. So we're just going to do 80/20 because we thought that was the best option. And for this one, we kind of made it really strict. We only did one fold, so we only folded the data set one time for each algorithm. So for each algorithm we pick, it'll just use basically train it one time for that fold. And it does pretty good here. I want to zoom in a little bit. Um, okay, that's okay. You guys can still kind of see it. It's pretty good, but definitely can be better. It's like here, there's still some errors. And now here, this is with three folds, and this is a lot better. I mean, there's still a little bit of errors, but it's really interesting how you can see the general shape. Oh, oops, the general shape of the cartilage, it's predicting where even the cartilage of the tibia is, which is interesting. And now for more results, I found these results to also be pretty good. And why is it so zoomed in? I actually kind of want a little zoomed in. But here, these are a lot better. And as you can see, it produced an accuracy of 99.75, which That's good. I mean, that's it definitely like if we in the future we want to optimize hyperparameters of this because we had to, yeah, but anyways, accuracy is pretty good. Just
The
Adam,
last thing that we did was we wanted to look at some other algorithms for like kind of our additional tools and the next steps of this project. So if we treated each voxel in our data set as its own feature, each sample has about 1.7 million dimensions. So the first thing we did was we used t-distributed stochastic neighbor embedding to reduce the number of dimensions in our data set from 1.7 million down to 2 dimensions. And then we fed those 2 dimensions into a soft margin support vector classifier to see if we could get our model to tell whether each MRI was a right leg or a left leg. And those results are shown over on the right. So we're looking at the plane represented by the two SNE variables and then the decision boundary of the support vector classifier. And we can see that it is able to relatively well tell the difference between a right leg and left leg. This is not a terribly useful thing, but we are going to adapt this once we get the rest of the data from the MyOB lab to kind of turn this system of dimension reduction and support vector machines into a tool for predicting osteoarthritis risk.
Okay, so finally, we don't have a ton of time left, but overall conclusions, UNet is 98.883% accurate, which is good, really good, obviously. And MONAI is just a little bit more accurate than that at 99.75. So another thing we came from this is that TSNE is really effective for analyzing our high resolution, high dimension image data. And as Adam said, that's going to be really useful for when we get more data from the MyOB lab. As right now, we don't have a ton of data, but in the future we want to modify, the architecture of UNet, integrate UNet into our MONAI system because you can use that and integrate it with the algorithm ranking thing. So we're going to try and do that, and we're going to keep working with MyOB lab to develop prediction tools for possibly osteoarthritis risk, like the volume of the knee cartilage or the roughness of the edges of the knee cartilage, which I think would be a really cool future task. So thanks for watching. Here are the references. And anyways, au revoir. Wait, I gotta stop recording.